Hello friends. Let us find the exact solution of this nonlinear differential equation. At first, we reduce the order by substituting dy by dx as p. Then d to y by dx to becomes p times dp by dy. Substituting into the original equation gives us a first-order differential equation in p and y. We divide both sides by p to simplify the equation. We now substitute p squared as w to make the equation easier to integrate. This leads to an expression involving dw by dy. Multiplying through by to square root w simplifies the equation. This is a linear first order ode in w with respect to y. We find the integrating factor, which is y to the power minus 4. We multiply the differential equation by the integrating factor. Now the left-hand side becomes a total derivative. We integrate both sides. Multiplying through by y to the power 4 gives the expression for w. We now return to the original variable dy by dx. We separate variables to integrate. After simplifying the left-hand side, we get a standard integral. We use the substitution y equals 1 over root c times sine hyperbolic of u to evaluate the integral. We substitute into the integral using y equals sine hyperbolic u over root c. Simplifying shows that the integrand becomes 1 over sine hyperbolic u. The integral of 1 over sine hyperbolic u is the natural logarithm of the hyperbolic tangent. We replace u with the inverse hyperbolic sine of root c times y. Integrating and substituting back yields the implicit solution. We isolate the hyperbolic tangent term by exponentiating both sides. We apply inverse tan hyperbolic to both sides. We isolate y by applying sine hyperbolic to both sides. We simplify using the identity for sine hyperbolic of double angle in terms of tan hyperbolic. Substituting tan hyperbolic inverse with exponential form gives us this rational expression. Substituting and simplifying gives an explicit expression for y in terms of x. This is an exact solution to the given nonlinear differential equation. Thanks for watching this video.